So if you're studying analog IC design or RFIC design, you might have come across a statement that says something like the noise performance of the first stage matters the most. So what does that exactly mean? Here, I have an example of an amplifier. So let's say that this amplifier has a gain of G, and let's say the output noise of this amplifier, is Vn out mean squared. So that's how I denote the output noise of this amplifier. And then let's say I take this amplifier and cascade it with another amplifier that has a gain of A. Now, let me just draw this and let me call the first amplifier amp1 and the second amplifier amp2. Now, what would be the input referred noise due to amplifier 2? Well, the input referred noise is the output noise divided by the gain, right? So that would be the output noise due to amplifier 2, which is Vn out squared, divided by the gain, which would be the gain of amplifier 2, the gain of G, but also the gain of the preceding stage, which is the gain of amplifier 1, which is A. And so what does this equation for input referred noise tell us? Or rather, what can we deduce um, from this equation? Well, we can say that if the gain of the first amplifier and the second amplifier, which is gain A and gain G, if these gains are high, then the input referred noise due to amplifier 2 would be low, right? And so we can say this. So now let's take an example of 3 amplifiers, right? 3 amplifiers in a cascade. What would be the input referred noise due to the third amplifier? Well, it would be the output noise of the third amplifier divided by the gain of the third amplifier, the second amplifier, and the first amplifier. So it would be even less critical. And you can think of 4 amplifiers in a cascade, and the output noise of that fourth amplifier will get divided by the gain of all the 4 amplifiers, and so on and so forth. And so by looking at this, we can basically say that the noise performance or the input referred noise of the first stage is something that matters the most, and the noise performance or the input referred noise of the subsequent stages or the successive stages would get divided by more and more gain. So it would be lower and lower and lower, and so hence less critical. And so if you have the first stage and if you have good noise performance, you have good input preferred noise for the first stage, then the noise performance of the stage 2, 3, 4, and 5, or and so on and so forth would matter less and less and less in that particular order. And so how is this knowledge, like, where can we apply this knowledge? Well, if you think of a two-stage op-amp, would it be fair to say that this is basically a model for a two-stage op-amp? Two-stage op-amp, right? So basically a two-stage op-amp is nothing more than, the first gain stage and the second gain stage. And so, when I make a later video about op-amp noise analysis for the two-stage op-amp, we will make a point out of it that, the noise of the second gain stage is less critical because it gets divided by the input referred noise of the second stage gets divided by the gain of that stage, which is stage 2, and also stage 1. And so that's a practical example of why the noise performance of the first stage would matter more than the second stage. Now, if you're coming from an RFIC background or just RF background in general, you might have heard about the freeze formula for noise. And so the idea is similar. If you have 3 amplifiers in a cascade, let's say with a gain of G1, G2, and G3, and each one of these amplifiers have a noise factor of F1, F2, and F3, then the freeze formula says that the total noise factor would be F1 plus the noise factor of the second amplifier minus 1 divided by the gain of the first amplifier. And then the noise factor of the third amplifier would get divided by the gain of the first two amplifiers, and so on and so forth. And so you can see from this equation that the noise factor of the first amplifier is what would matter the most, right? Because the noise factor of the subsequent stages are getting divided by the gain. And so this is why it's very common in like RF transceivers to have an antenna, but the first component in the signal chain would be something like an LNA or a low noise amplifier. The whole point of that LNA is to add a gain, a good gain, but also add as little noise as possible so that it achieves a good noise factor and by extension a good noise figure. And so as long as you can do that, then that relaxes the noise performance of the subsequent chain, the subsequent stages in the RF chain.